Now I just want to briefly introduce this notion called a unimodular group. Okay, so by definition, this unimodular group is essentially just when your modular function we introduced last time is constant 1. Okay, so a group is called unimodular if the modular function is always 1. And just some quick propositions. So if G is any one of these 4 categories, then it's unimodular. Okay, there can be more, but let's just do these 4. All right, so first of all, if G is a billion, so let's do the proof. All right, so I want to show that if G is a billion, then it's unimodular. Well, that's kind of trivial from just the definition. So if you recall, the unimodular function comes from the difference between the right translation of a left Harmonic. All right, but the left translation is, well, because it's a billion, so right translation is also left translation, and it's a Harmonic, so it's basically invariant on the left. So this implies the delta has to be always equals to 1. Okay, so that implies delta is always equals to 1. Second, let's show that if G is compact, then it's actually a unimodular. And in fact, there's a stronger result if I have a compact subgroup. Okay, then my modular function restricted on this compact subgroup has to be equals to 1 as well. So let's just prove that instead. All right, so if K is compact, then what we have is that we know if I consider delta from K to the product, the multiplicative group of the real, the positive reals, well, this is a continuous map we saw from last time. So in particular, we know the continuous map maps compact sets to compact. So this is going to be a compact subgroup. Okay, so that's a compact subgroup of this 0 to infinity. But if you think about what happens in the 0 to infinity, as long as you have something that's not equal to the identity, well, then these powers will either converge to 0 or its negative power will converge to positive infinity. Okay, so either you have something greater than 1 and it's keep multiplying it, you get something goes to infinity, or you get something less than 1 and its negative power goes to infinity. So you never get a compact subgroup. The only chance you have a compact subgroup is just the identity element. Okay, so the only compact subgroup of the multiplicative real is just the identity, okay, or constant 1. So in other words, the delta restrict to this K is just equals to 1. And of course, when G itself is compact, you also have this is equals to 1, okay? The third one, when G is discrete, it's kind of trivial. So when G is discrete, then all your singleton set is both compact and closed. And you can convince yourself a counting measure is both left and right in hard measure. Okay, so and that's actually only multiple of them are all the hard measures. All right, so basically from there you know that well, because it's both left and right invariant, there's clearly a unimodular group. Okay, so let's just say counting measure on a discrete group. Our discrete group is left and right hard measure. Okay, so it follows quite immediately. And the last one, I want to show that if your G, if you quotient out this commutator subgroup, if this quotient is compact, then you have something that's also unimodular. Okay, so let me just remind you this G, the commutator group is basically generated by those commutators X and Y, where XY is inside G. Okay, so this commutator is essentially just XY, X inverse, Y inverse. Okay, so when X and Y are abelian, then clearly this commutator is identity. Otherwise, it kind of measures how non-abelian they are. But anyways, if you consider what happens if you evaluate on this XY, and because delta itself is a group homomorphism, you have S equals to delta X, delta Y, delta X inverse, delta Y inverse. And because the range of this delta is the positive real, so it's abelian, so all of these will cancel out and will give you 1. Okay, so your delta, when you restrict it to your commutator group, is certainly equals to 1. Okay, So you can think about it as your delta function is in the kernel of your map from G to the positive reals. So it certainly factors through this quotient. Okay, so delta factor through your quotient map, G mod the commutator group. So in other words, you can have a delta, let's say delta bar, from the commutator group, the quotient by this commutator group to the 0 infinity. That's also a group homomorphism and continuous. All right. Well, this may not be the modular function for this group. Okay, just let you know, because if that's the case, then you mod out the commutator group, you have the abelian, then abelian group are unimodular. Okay, that's not going to work. All right, so this is just some continuous group homomorphism from this quotient group. Okay, and we know this quotient group by assumption is compact. So we know that this factor, this restricted map, this delta bar is going to be always equals to 1. And then that basically just tells you delta itself has to be equal to 1. Okay, so G is unimodular. Okay. All right, so let's finish the proof of this proposition. I just want to point out as an application of the last point we have here, it actually tells us about something in Lie group. I'll just write it as a fact here. So in fact, if you have a G that's a semi-simple, meaning it's a direct product of some simple Lie groups, and it's connected, okay, just means connected in the topological sense. If it satisfies semi-simple and connected, then it's going to be unimodular. Okay, so G is unimodular. Okay, so this is use some fact from the Lie theory. Okay, so this course is more focused on the analysis on groups, so I'm not going to touch too much into Lie group. If you're interested in learning more about Lie group, we do have a course, I think it's 763, talking mainly on the analysis on Lie groups, and talk about the relation between Lie group and Lie algebra. And of course, Haar measure is also a quite important thing in that course. And you will learn about that, more about that in that course. Okay, so I'm not going to go into any more detail on this Lie group. Okay, so these finish our example of the unimodular groups.